Thank you very much for coming to the talk today, using dots to optimize GameObject gameplay, a case study for survival kids. I realize I made a bit of a mistake with the session title in that I chose a title that was alphabetically last of all of the sessions. So well done for scrolling through all of the other sessions to bookmark mine. So quick introduction before we get going. My name is Andy Bastable. I am a staff software engineer at Unity Studio Productions. I've been in the games industry making games for about 26 years, which I think means I qualify to be called a veteran these days. Certainly means I'm very old. At Unity Studio Productions, I've had the privilege of working on a lot of customer projects, helping them to solve gnarly technical issues. And for the last couple of years, I've been part of the internal game development team at Unity that worked on the game Survival Kids that hopefully you've already heard and seen a lot about. So just a quick run through of what to expect from the talk today. I'm going to talk a little bit about Survival Kids, the project, its constraints, what the vision for the project was, how it came about. And then we're going to really, the meat of the talk is about how we can use the other bits of dots to power GameObject gameplay. By the other bits, I mean the bits that aren't entities, basically. So the other aspects of dots, and I'll explain a little bit about what those are as we go. Interspersed with all of that will be practical case studies from some of the problems that we had to solve when we were developing Survival Kids. And then at the end, hopefully there's a bit of time for questions, so that should be quite good. I should warn you, it's quite dense. There's lots of code. I'm going to be going quite quickly through a lot of the code, so don't worry if you miss it. Just make sure you catch it then when it's streamed online, and then you can follow along. So Survival Kids, the game, we've already heard a lot about it. Survival Kids was the very first full game development that we've done here at Unity. It was fully designed and developed at Unity, right all the way from conception to delivery. And we were very proud to work in collaboration with our publishing partner, Konami, to bring this project to life. And we delivered it as a day one release date launch title for the Nintendo Switch 2. So part of the reason why we worked with Konami on this was we wanted to have a development relationship and a development life cycle that is exactly like the kind of relationship that you guys have when you're making your games. So we had a very traditional developer-publisher relationship. We were an internal game studio within Unity. We worked with Konami to set publisher milestones and deadlines and deliverables. We had to make those deliverables, and that meant we had to solve the kind of trade-offs and constraints that you guys have to do all the time. Well, when you have a delivery, do we upgrade the project or do we stay on the version that we are? How much risk do we want to take on? Do we want to use this technology or do we want to use that technology? So this wasn't an internal project with no end dates. This was a very fixed commercial product, which basically meant we had to live the journey that you guys have lived all the time. The game itself is a crafting and survival game for up to 4 players. Co-op really is at its heart. You can play it single player if you haven't got any friends, but it really, really kind of sings when you play it in a co-op way. That can be local co-op, split screen, but also online game modes as well. And as you've all no doubt heard through the keynote and through the product roadmap, product verification is at the key of really what we're doing at Unity at the moment, and this was a big part of it. So throughout the development, we made sure we fed back to all of the teams when we had pain points, when we struggled with editor upgrades, when we found packages that were unfriendly, we discovered bugs, we were then able to take the fixes and validate the fixes. So this was a living kind of life cycle. And even more so, the project lives on even now. So even though it got released, that project is continually upgraded, and other teams are now using that project to verify new changes that are coming through to check that they solve actual problems that we encountered along the way. So I'm just going to show a super quick video. It's a trailer of the game, just in case you haven't seen it, so you can get a feel for what the game is like. So not only is it out now to buy on the Nintendo eShop, but it's also getting a physical release in Europe just in time for Christmas. And what a lovely Christmas present that would make for anyone you know who has a Nintendo Switch 2. Let's make sure. So just a little quick overview about some of the technology that we did. I should say, by the way, that because it's got kids in the title, because the visuals are very approachable, people tend to think it's a children's game, a game aimed at children. It's not. But family and being able to play with your friends really was at the core of what we wanted to do. We wanted to make it an approachable game. So we shipped the game on the publicly available version of the editor, Unity 6. In fact, we always used the public versions of the editor. We never used any source control modifications. We didn't have any secret source. So we just used the same kind of technology that you guys would use. And that was the same for the packages as well. So we didn't use custom versions of the packages. We didn't tend to make modifications. We tried to, say, live the kind of journey that you guys have to live all the time. Our co-op solution used netcode for entities under the hood. That was as much far as we went with entities, but we did write a custom game object layer on top of it, which we call our Ghost Bridge. It was mentioned in the keynote that that's actually available in the Unity 6.3 starter assets that are coming up, the building blocks with the first-person sample. So you can actually find that kind of networking layer that we used and that we proved out through the release of Survival Kids. In addition, we also used Lobby and Relay from the Unity gaming services as well, and that served us really well. The graphics, it won't surprise you to know, you probably guessed that it's URP. We had some custom shader graph in there as well. We used adaptive probe volumes for a dynamic day and night cycle. We didn't actually ship the dynamic day and night cycle in the end, because it didn't actually fit the game design, but all of that code is still there, and there's a nice slider that we can do. And we set ourselves quite an aggressive target of 60 frames a second on Nintendo Switch 2, which we were very proud to have achieved. So why is it good a case study for what we're going to talk about today? Well, in a typical level, some of our bigger levels, there are over 1,000 game objects in the scene. So this is a typical kind of scale that you might have on a slightly larger project, maybe kind of a medium like single A, double A style. We had real world trade-offs and the deliverables that we had to hit. So that meant when we had to hit our deliverables, we had to hit our visual quality and our performance metrics. So we were constantly optimizing as we went. And then, like I said, we use the public editor and the packages as well. So everything that we talk about here is available for you guys to use as well in your projects. So worth doing a quick overview about DOTS. We all kind of know that DOTS stands for Data-Oriented Tech Stack. This was something that we introduced back at Unite many years ago now. But when we think of DOTS, I think a lot of people straight away assume that DOTS is entities, that DOTS is ECS, but actually DOTS is an umbrella term for a whole bunch of different systems that you can use. And what we're really going to be focusing on is the ones that are in the list here. We're going to be talking about systems, which are systems that can update. We've got the burst compiler. So this is a way where we can have vectorizing code that works on multiple data at the same time. Jobs, which allow us to use worker threads, move stuff off the main thread. Native collections, and then TransformAccessArrays, which are a kind of a special form of native collections and jobs. If you're all here for an optimizing talk, hopefully you know all of this already, but the tools you need if you're going to do any kind of performance work, any kind of optimizing, use the Unity profiler. It's built into the editor. You have no excuse not to use it because it's really easy. If you're not using it, I highly recommend that you download the Profiler Analyzer package as well. It's a Unity package. It's free to download. This allows you to capture and analyze a trace, like a series of frames in the profiler, rather than looking at one individual frame. It can aggregate a large amount of data and give you insights. Even better, you can compare two traces and see what has changed between them. And if you're developing on a device, mobile or console, then always make sure you use the native profilers that come with that platform as well. So these are PIX or the Nintendo CPU profiler or third-party sampling profilers like Superliminal. Okay, quick disclaimer, I'm going to be showing lots of profiler traces. All of the performance captures were taken from a Windows workstation and a Windows development build. So that means the numbers aren't necessarily representative of target hardware. And obviously, these are the case study numbers that we got in our project. It's not necessarily representative of what you might get in your projects because everything differs by project and by environment. Hope you're okay with that disclaimer. So we're going to start with our very first topic of today, and that is how we can use systems to update MonoBehaviours. So let's talk about MonoBehaviour update. So hopefully most of you are familiar. You create a class you derive from MonoBehaviour, and you just add an update function. And that update function, from that point on, is magically called for you every single frame. You don't have to do anything to have that happen. Just the act of creating an update function will mean it automatically gets updated. That update happens in a fixed location in the frame. If you've ever looked at the Unity profiler in that way, you can see it under Behavior Updates. That's where all of the updates happen. Now, the problem with the native MonoBehaviour update is it's a potentially random execution order. So there are some levers that we can pull to try and wrangle it under some control, but largely we're at the behest of whichever order the game objects were created and the components are on the game object. This means that we can't always guarantee that we are updating our game objects in a way that is optimal for cache. Now, if you're at an optimizing talk, I'm going to assume that you all have a little understanding about what CPU cache is, but just so that I make sure everyone's on the same page, modern hardware has CPUs that do all of the work, and then we have memory that is often located somewhere else on the system. And the CPU, when it has to do some work, has to go over to the main memory and pull that data back. Rather than doing that round trip all the time, it stores that data that it has retrieved in cache. And there are different kinds of cache, often very small but very fast, and then some slightly larger cache that's there. Now, we find that there is a big speed up if you can be working on data that is cached. How fast? Well, here's a little illustration of the orders of magnitude. This was a tweet from a few years ago. L1 cache is a beer in hand. L2 cache is a beer cooler by the sofa. L3 is going to the fridge. Main memory is walking to the store. And disk access is flying to another country for a beer. Now, actually, the disk access is probably true if you've got a fast SSD. If we're talking about a mechanical hard drive, you're actually flying to another country and staying there for a couple of weeks. That's the order of magnitude that we're talking about here. Effectively, we want the memory that we're accessing to be in cache as much as possible. L1 and L2 tend to be quite small, but modern hardware actually has quite a generous amount of L3 cache. So we're going to find out that by changing our update order, we can start using that to our benefit. Systems to the rescue. So we can use systems to collect and update our MonoBehaviours. We can choose where they update in a frame. And then we can sort the updates so that we have objects that are really similar, kind of updated together to see whether we can get some sort of cache improvement. For this, you're going to need the entities package. So it's scary. That is, if you don't want to use entities, you don't have to, but you do need the entities package, and that will automatically give you access to systems. If you do that, it will automatically give you the initialization, simulation, and presentation system groups. Now, system groups are effectively just a group in a frame that you can place a system and know that roughly it will be updated in that position in our frame. We'll see a little trace of that in a moment. So here's a typical frame. This is actually a capture from Survival Kids. And this just basically lays out the order in which things happen. So we can see right on the left, we have the initialization system group, one of the first things that happens in a frame. Then we have behavior updates. So this is where all of our native MonoBehaviour updates get automatically called. We then have the simulation system group run. Then we have late behavior updates. So if you're using late update in any of your MonoBehaviours, that's where they get updated. And then we have the presentation system group. And then generally, right at the end of the frame, you're going to have all of your rendering. So this is our CPU trace. Hopefully that's vaguely familiar for a lot of you. So we're going to create a system now that is going to collect and update all of our MonoBehaviours. So we're going to start off. This is how we create a system. If you've never done it before, we're literally going to create our system. We're going to call it MonoBehaviour Update System, and we derive from system base. Now, if any of you have done any entities work, you'll know that there is another way that you can have systems using iSystem. That tends to be for burst compiled things, so that's not really compatible with managed stuff, which is what we're doing here with GameObjects. So we're going to come from system-based. And we choose right at the top, we use the update in-group attribute to specify which system group we want that in, which is the simulation system group there. And every system needs an update function, because that's what a system is. It's a place to update things. If we want to move that system in a frame, we can use the update before and update after attributes. So if we had lots of systems in that system group, we can specify that we want to occur before or after a particular system. And if we've got lots of them, we can actually just arrange the order so that everything happens exactly where we want it to. Now we're going to make it a singleton. Now, I'm sure that there are some people in the room straight away wincing at the very thought of a singleton. The singleton pattern, generally it can be messy. There are some downsides to using it, but if it's done properly, it can actually be very useful, particularly in this case. What we need to do is we need something outside of the systems and the entities world to have access to our system. And so we're going to create a static variable instance. Well, when we create it, we're going to assign it to the system, and then when we destroy, we null it out. That now means that anything can statically use that instance pointer to access this system. Now, that is fine. However, if you are, as I hope you all are, running with domain reloads turned off in your editor, can I have a quick show of hands? Who has got domain reloads disabled in their projects? Brilliant. Everyone else, you need to go back to your hotels and have a good hard look in the mirror. Seriously, turning domain reloads off means you can get into play mode so much faster. You don't have to sit there looking at this reloading domains bar all the time. But if you turn it off, and you can go into your project settings, and then there is a play mode options, and you can tick off the reload domains. To do that, it means all of your static variables won't be reset between runs in the editor. So we need to handle that somehow. How we handle it is really easy. We just wrap it in a hash Unity editor, because this is editor-only code. We don't need to worry. Players don't need to worry about this. And then we can hack into this this callback, which is subsystem registration, which gets called really early when you hit play in the editor. And then we just reset our instance. If we don't do that, when we next play it, that static variable will still be assigned. So now that we've done that, we're going to collect all of our MonoBehaviours up. So we're just going to create a list, regular, normal list. We're not using native collections at this point. And then we just create a function, register, which is going to take a MonoBehaviour and it's going to stick it in that list. Now, it's pretty important to put those asserts in there, because you'd be surprised how often you get double registers and double deletes when you've forgotten to clean up something properly and then it registers again. So it's always a good practice to have those things in there. So all we're basically doing is we're just adding the things. And if we don't really worry about the order at this point necessarily, so we can just remove it, swap back. And then this is our MonoBehaviour, typical MonoBehaviour. This could be anything you want that you're updating. We've got our update function at the bottom. And so all we do is in our awake, we go and grab the update system via the instance, via the singleton, and we register it. And then on destroy, we unregister it. Now, because we can't guarantee the order in which things are torn down, we do need to check to see that that system's still there, because otherwise it's not. You'll get a null exception, red text in your console, and it'll make me very sad indeed. So do check before you unregister. And then we're going to call the update. So this is our system. We're going to just go through all of our updates, and we're just going to call the update function, because it's a MonoBehaviour. We know that update function exists. However, some of you will have spotted the problem straight away, which is now we're going to get two lots of update calls. So we're going to get an update call via our system, and we're going to get an update call via the automatic MonoBehaviour updates that get called. So this is not ideal. So how can we fix this? Well, ideally, what we want is to just rename that function, because if we have a function that we're calling that's not called update, then it won't get automatically called by the MonoBehaviour system. And so that will get us out of that. So how we're going to do that is we're going to create an interface at the top called iManualUpdate. And that just has a single function, manual update. And then our MonoBehaviour, not only does it derive from MonoBehaviour like you normally would, it also implements that interface iManualUpdate, and then we just rename the function from update to manual update. So that's all we do. It's the same function. It's doing the same things. We've just renamed it. And that means instead of collecting our MonoBehaviours, now we're just collecting the interfaces. Which has the added benefit, by the way, of meaning it doesn't actually have to be a MonoBehaviour. That we can collect anything now that has an update function. We just provide that interface there. That means on our update, we just go through and we call manual update, because we know that exists. And so now our updates are all happening through the system, and they're not happening through the automatic MonoBehaviour calls. So does the update order matter? Some of you might have been a bit skeptical. The answer to everything, and any senior engineer will always tell you this, is it depends. It really depends on what you're doing. It depends on what your MonoBehaviours are doing. Are they accessing shared memory? Are you running at scale? Do you have a lot of these things? If you do have them at scale and you have a whole class of GameObjects and MonoBehaviours that are generally doing the same sort of thing, then my experience is yes, if you change the order so that you're updating all the related things together, then you will see a speed up in terms of execution. But we can test it. So imagine we've got 3 different kinds of objects, A, B, and C. These could be AI agents, they could be physics-based collectibles, they could be UI elements. They don't have to be particularly game objects. They can be, they don't have to be like elements that are actually in the game. But they're doing different things is the crucial thing. So in our unsorted example at the top, they're just in a random order. Maybe some of them are together, but often they're going to be interleaved. But if we could sort them, and if we sort them, that means we update all of the A's together, then we update all of the B's and all of the C's. Now, how you update, how you sort them, how you choose to order them, that's really up to you. So you could do it on type, you could do it on the MonoBehaviour update type, group all of those updates together, or you could do it on GameObject. You could go, I'm going to do all of my AI agents together. I'm going to do all my HUD elements together. That's entirely up to you. On Survival Kids, we actually did it on object type. So we updated all of our objects, our game object types, and then we went through the updates for them. So how would we sort it? This is a nice little way. We did this on Survival Kids. Rather than sorting it every time that we register and unregister, because sometimes you're going to spawn or destroy multiple things in a frame, all we do is we set a flag that the list is dirty, and then when we get to the next update, if that's true, we just sort the list based on whatever heuristic we've chosen to do. So we then have a nice sorted list. So does it make a difference? Here is the Profile Analyzer tool. If you've never seen the Profile Analyzer tool before, let me explain how it works. The top trace is a profiler capture from before. So from before I did the optimization to sort our game objects by type. So that's the top one, and then so that's blue, and then red, the red bar, which is the next one, is when I've made the optimization. And then we can see these charts down here, and they basically show the difference between executions, aggregated. So we can see that the unsorted updating took about 0.99 milliseconds, about a millisecond to update all of our objects that we've got. And there's a particular marker that we're tracking down there for that update. The sorted update, so sorting them by type, gave us 0.87 milliseconds. So a bit of a speed up. And if you click on a marker in the Profile Analyzer tool, it will give you a little breakout kind of special detail about that particular marker. And on here, we can see that the red was better, lower is better, it's faster. But we can see that on the average frame time, we can look at the median and the mean times, we had a 12% speed up. And in our worst case frame, so the slowest frame, we went from 2.18 milliseconds to 1.43 milliseconds. For a 60 frames a second game, that's huge. That's like a huge thing. Now, I want to stress, we haven't changed anything in the algorithms. We're not doing any different updating. We're still doing exactly the same thing we were doing. The only difference we have done is we've changed the order in which they're updated so that they are updating, and we've got a chance that these things are going to be in cache. The shared memory is going to be in cache when they do them. So that is definitely something you should consider doing. So the next thing we're going to talk about is using TransformAccessArrays. Quick show of hands. Anyone use TransformAccessArrays here? Surprising amount of people. I like it. So TransformAccessArrays are a special kind of native collection that collect the transforms and then allow us to use it on worker threads, but also to potentially use bursted jobs with them as well. So the problem. Sometimes when we're updating things, we need to access game objects. And if you access game objects or any generally Unity managed object, that has to be done on the main thread. If you try and do it on a worker thread, you'll get exceptions. But sometimes we only need the transforms. Like sometimes we just want to aggregate and collect a whole bunch of transforms and positions, and actually we don't necessarily need to be on the main thread for that. So could we move that work to the worker threads? Why would we do that? Well, here's a little trace that makes me sad, very sad. This is actually from Survival Kids, so I'm complicit in this. The main thread is pretty saturated with lots of jobs. You can see it's doing lots of jobs there. And then the worker threads, they've got a little bit of work, but there's all of these gray areas that are just idle. The worker threads are sitting there not doing anything. And this is really typical of a Unity game, which tends to be very main thread heavy, particularly if you haven't put the work in to move some stuff off the worker threads. Can we make that any better? So if we use TransformAccessArrays, it means we can access transforms in a bursted job, and we can move it onto worker threads. Now, there are some constraints on when we can use them. If we're moving stuff onto a worker thread, that basically means we can't really access the same memory that the main thread is using. And the transform system will manage that for us. So it will block the main thread if that's what we're doing. So as a general rule, if you're using TransformAccessArrays, don't use transforms in the main thread. There are some nuances to it. There are bits of the hierarchy that you could use TransformAccessArrays with whilst you're still the main thread's doing something. But it's a hassle. Just don't do transforms on the main thread while you're using TransformAccessArrays. So here's a case study. This is a real-world example that we had on Survival Kids. So we have UI elements. Our UI elements tend to be positioned over in-world game objects. So this is not world space UI. Those UI elements don't live in the environment. They're actually rendered with UGUI on a canvas that is overlaid over the camera. But in order for those to be in the right place, we have to transform those UI elements so that they stay rooted to wherever the object is that they're attached to. On a typical level, we might have 20 to 50 HUD elements. Sometimes they're crafting pop-ups like you see here, but sometimes they might be status effects like stamina or health over a player, or they might be an emote that they've placed down. They tend to be they represent a world object that they're attached to. Now, we transform them using a function which some of you will be very familiar with, which is called camera world to viewport point. So this is taking a world space and it's projecting it onto the screen and saying this is where it belongs on the screen. Now, when we have that, elements are either culled if they're off screen, so we just disable them so we don't have to pay the layout cost for them, or sometimes we clamp them, so we might rotate them. If you have like an objective arrow that's pointing somewhere, that's the kind of thing that might be clamped off the screen. Now, crucially, we have to do this transform for every gameplay camera that we have in the scene. Now, you might be thinking, well, that's fine. You've only got one camera there. But we have split screen mode on Survival Kids. On Nintendo Switch 2, we shipped with a single player, a split screen with 2 players. But we used our split screen technology to drive our Nintendo Game Share facility. So this is basically where instead of rendering it onto the screen, it's taking the results of that camera and streaming it to another console, another Nintendo Switch 2 or a Nintendo Switch. So this can run on a Nintendo Switch as well. So we never used the 4-player split screen. We didn't ship with that, but internally we kept that 4-player mode so that we could stress test all of our systems and check to see that they worked okay. So for every HUD element that we had to transform, we have to do that 4 times. For 4 cameras, we need to duplicate all of those elements and we need to do it 4 times. So camera world to viewport point, you may have used it without thinking about it too much. There's very similar ones to these that go both ways. This is a manage function. So it lives on the camera object. You have to call it on the camera object. So you need to provide it a camera. This straight away is a barrier to us moving this onto a worker thread. Okay, it must be called on a main thread. But effectively, what it's doing is really well understood matrix math. It's just using a projection matrix to transform some stuff. So we had the advantage of being able to use Unity source to figure out what the maths are doing, but you could just ask your favorite large language model. It'd do a pretty good job of giving you the source that you need to do for this. It's very well understood. So this is what it looked like before we did any kind of optimization. This is actually taken from our game development. So right at the start, we actually do a HUD culling pass. This actually used the results of the previous frame. So this was basically looking at transform positions. Are they off screen? Shall I disable them? Shall I enable them? And then the actual transform, the transforming our HUD elements happened right at the end. It took 0.75 milliseconds. So the whole thing took about 0.9 milliseconds. This is on a fast Windows PC, by the way. So you can imagine that an order of magnitude longer on the consoles. So when we're trying to hit 60 frames a second, we can't really afford to be spending almost a millisecond on transforming UI elements. So let's improve things. What we're going to do, and I'm going to talk you through how we do it, we're going to collect all the transforms that we need up front. We're then going to use a burst compile job to do all of that work to transform it for us. Then we're going to run that on a worker thread, and then when it's done, we'll grab those results on the main thread and we'll apply them back to our elements. Let's go. So we're going to create a new system. You all know how to create systems now because I just showed you the first time. So we're going to create another one. It's on the simulation system group. We're going to call this update HUD element systems. We've created a little struct there. Now that struct is an intermediate struct. It's just where we're going to temporarily put our results. Because if it's a struct and if it's in a native array, that means we can do a bursted job that can just chew through that really, really quickly. So that's what we're doing there. And then we've just got our onUpdate function. So we're going to create our TransformAccessArray. TransformAccessArray is just there. We called it mTransforms. And then what we're going to do is, I'm doing it here on our update function. So every frame, I'm collecting the transforms and putting them in the TransformAccessArray. That's only really appropriate if you've got a dynamic thing where you've got lots of different numbers of transforms because things are being created and destroyed. If you've got a static number of these, you don't need to do this every frame. Just do it when you've got all of the transforms, put it in there and forget about it. Don't have to do it anymore. But if you need to do it, this is how you do it. So we're just going to call a function collect transforms. Imagine this is that you maintain a list of all of the transforms you need. What I don't want you to do is go off to the hierarchy and just go find all objects by type transform and get everything in there and throw that in. That's how you're going to tank your performance and make me very sad indeed. So imagine you're just going to get a list. And then once you've got those transforms, if it's created, you just set the transforms. It's just going to update them. Otherwise, we're just going to create a brand new TransformAccessArray. And then because it's a native collection, that means that memory has been allocated, which means we need to dispose it again at the end, like good citizens. And then we're going to create a job. And the first job we're going to do, all it's going to do is copy the positions into our native array, our struct. So here we've just got a burst compile job. So the burst compile attribute at the top is important and means it can go fast. And then our execute is going to take a transform access, which basically represents a GameObject transform. We need to check that it's valid. So if we're destroying transforms, that's effectively like checking it's not null, which might happen. So just check that it's valid. And then if we do that, we're just going to create a brand new HUD element with our flag in. So all we're doing is pulling the data out of the transform system and inserting it into our thing. Now we're going to have a separate job in a minute that's going to apply, it's going to actually do the processing. The reason we're doing this, the reason we're getting all the transforms out and putting them in an array is we're doing it as quickly as we can so that we're not locking the transforms from other stuff doing it. So if all we're interested in is reading the data, we just grab it quickly and then allow the main thread to carry on its merry business. And then we schedule the job. So in our update function, we call, I should point out that this is using an iJob parallel for transform. It's a bit of a mouthful. It's a special transform version of an iParallel job. So yeah, we schedule it here. So we create an element, we create our job, we pass in the native array we're going to write to, and then we call schedule read only. We're only interested in reading here. There is a schedule version if you want to write to it as well. We pass in our TransformAccessArray, and then the number here is the batch size. So if we do a small number, then if we have a number of transforms that exceeds that, it will then put them into separate jobs, each doing just that batch size. But actually, this is blindingly fast, so we might as well just let it go in one job because it's going to be quick enough. And now we're going to create another job. And the jobs are actually going to do the work. So now that we've collected all of our points that we want to transform, we're going to do another job. And this one is called Transform HUD Elements job. It's going to transform them. Again, it's burst compiled. And we've got a bunch of read-only components that are using, they're using unmanaged types. So they're using rect and they're using float 4x4 matrices, effectively. And then we're passing in our elements that we originally had filled up. And all we're going to do here, this is one job. We're not parallelizing. This is one job that's just going to run on a worker thread. We're just going to go through all of those elements. We're going to call our special handmade version world to viewport point that's going to do the transforming for us. And then we're going to write it back. And we're going to do a quick check. Is it on screen? Is it within the camera viewport? If it is, brilliant. If it's not, then we're going to set a flag is element off screen, which we can then use to disable the game object if we want to when we're out of it. And then once we set that, we're just going to write those elements back to the native array. So we're going to schedule it. We've already got our copy transform positions. So all we're going to do, we're going to grab that handle from that job, copy handle, and then we can pass it into the following job. So we can schedule it using that job handle. And that means as soon as this first job is done, the second one will be allocated and can go off and do its thing. So that's just going to go. That's all going to happen in a worker thread. As you can see, we've grabbed the camera and we've just pre-passed in all of the matrices that we need. So the jobs themselves don't need to do the camera lookup all the time. So when you're normally doing it, you're having to go and get the camera and all the stuff. So if we want to use those on the main thread, so once we've done it all on the worker thread, it's gone off and it's done its work, and eventually we want to use that native array again, then we need to call this function complete. We need to store the handle of the job, and then we need to check to see that it is complete. And we need to do that even if we can see on our profiler that that worker job has finished. So if we're looking at this job and we can see that it's finished, we still need to call .complete on the main thread. If it's complete, that should be a very, very fast operation. If it's not complete, it will stall the main thread until it is. But it will complain about you accessing the memory unless you do that. So we just have an accessor, and we're just going to call .complete. If it's already completed, it'll be a very quick operation, and then we can then access all of the bits. So how might we apply those? How might we actually then apply it back to our game objects? We could use a transform access array. Here we're going to do it the traditional way. We create a new system, another system. We're going to update it after some systems. Not just, we don't want it to run straight after our first system because it's not going to, the worker job's not going to have enough time to do. So ideally there's a bunch of other work that's happening at this point. But at a later point, we just have an on update. We go and grab our processed HUD elements, and then we just go through and we go and set the transform. So imagine we've got our list, our collected HUD elements. We're just going to go and set our transforms out there. So effectively, all of the hard work, all of the transforming has been done on a worker thread, and all we're doing is literally setting the transform there. And we might look at the element like is off screen, we might just kind of use that to enable the game objects. So in practice, so this is transforming 500 HUD elements. So I said our average cost was like 20 to 50. This is 500, 4 cameras. So the system that's scheduling everything took 0.009 milliseconds. That's a rounding error, that's fine. And then the copy job was 0.03 milliseconds. The transform was even quicker, because once it was in a native array, once we're just doing a bunch of maths, Burst can do its thing, which basically means it can vectorize it and do it really, really efficiently. So the whole thing was done really, really quickly. Now, we are doing this with .schedule, so we're using the worker threads, and that's entirely what you should do. But sometimes you may find that it's easier to just do .run. So burst jobs can still be run on the main thread. So you can do a job in exactly the same way. You can have burst compile, but then instead of using .schedule, you can do .run. This avoids us needing to call .complete at the end, because everything's happening on the main thread. And this is particularly useful if you spot gaps in your profiler where the main thread is stalled waiting for other things. So here's an example. So we use netcode for entities. Sometimes the game's running so quickly that one of the processes is waiting for network transfer. So it's waiting for a packet to be decrypted or something. We can see here we've got this big green worker bar, and the main thread is stalled. We can see there's almost like a kind of a dusty yellow marker, and it says waiting for job group ID. It basically means the main thread is waiting now for that job to be complete. If we spot stuff like that, we can schedule, we can move some work there, and then we just get free performance, because the main thread is just waiting. So we might as well put some work there if we can. And that's exactly what we did on survival kits. So on this one, we actually went just on the main thread. We didn't need to use worker threads. But as you can see, we're doing this 4 times, but each one is lightning fast. The building the list, which is exactly what we just showed, 0.04 milliseconds. The processing, 0.01. And then applying that was also really quick as well. So the total cost for all 4 cameras was 0.21 milliseconds. So that was faster than the original, but we were also throwing more UI elements in it as well. Some other uses you might want to use as well. You can use it We use it for writing network transforms. So because we have a system that is using net code for entities, but with a GameObject layer on top of it, we often have to pull that data out of the net code system and apply it to GameObjects. So we just use TransformAccessArrays to do that really, really fast. We also have a system for what we call dormancy, which looks at player proximity. So this is, we've got a lot of very expensive updates. And if the player is nowhere near them, if they're off screen, we just don't need to update them at all. So we have a system that runs in a worker thread that just basically calculates how close they are to the players. And if they're far away, we just disable their updates. So we just don't have to pay the update cost for them. And then we also use it, TransformAccessArrays, for building a KD tree for spatial queries, which takes me very nicely onto my next topic, which is you should use KD tree to optimize spatial queries. Now, KD tree is a system that I actually wrote a couple of years ago, so it's very good. It shipped as part of Megacity 2019. Confusingly, not the latest Megacity sample, because I didn't need to use it, but it's on the Megacity 2019 sample. Now, there's no documentation about it. There wasn't a forum post, but it's on GitHub if you know where to look. And I very handily put a QR code for you in a bit, so you can go and find it. We used it extensively in Survival Kids. It's also been used in a number of other projects. So it is a shippable technology that we have used to optimize our spatial queries. What do I mean by spatial lookup, spatial queries? I mean effectively answering the kind of question which is, give me the 10 closest items to this point in space. Give me the 10 closest objects, the 5 closest objects. Is there an object of this type close to where I am? That's the kind of thing that a KD tree can optimize very well. So let's create a simple toy example. We've got a simple cube. By the way, this scene is actually what we call our playground scene. So this is where we've got all of our different possible items in the game. Was never shipped as part of the game, but it was what we used for our development environment. So we've got a toy example, and this is a simple cube that is going to change color if an item becomes within a certain range of it. In this case, we're using a carryable, which is a log. Doesn't matter whether it's placed on the floor. If it's within range, it changes color. So this really is a toy example, but it does represent the kind of gameplay challenge you might have. It might be an AI agent who needs to know if there's a particular kind of player or item nearby, or it might be a pressure plate or something like that. Now, you might be tempted to think, I'm just going to use a collider for this and a trigger, which is the typical way of doing it. But you should know that if you use physics for this extensively at scale, you're going to pay a cost for that. So every time a collider moves, you pay a cost for updating the transforms for that, for using physics for this kind of thing. So if we can avoid doing that, then we should totally try. So how might we do this without using physics? A really naive way of doing it might be to do it like this. We have a function isItemInRange. We're going to collect all our items. Again, I'm assuming that we just maintain a list of the kind of items we're interested in. We're not doing find objects by type here. And then other than that, this is pretty optimal. So we're not doing a distance check. We're doing a squared magnitude, because all we need to know is a radius check. So it's pretty optimal. But we're just going to go through all of the items on that list. If they are within radius, we're going to return true. Pretty simple. So what does this look like when we captured it? So I simulated it. I dropped 20 of these cubes in one of our levels in Survival Kids. There were 1,000 gameplay items. This is a typical gameplay level. We can see that each individual cube took about 0.24 milliseconds. Now, interestingly, the eagle-eyed of you would have spotted that I actually used the second cube, because they're all updating together in a line, because we know how important it is to update things that are related. The one before it takes about 4 times as long. Why does it take 4 times as long? Because it's not in cache. It's not using the cache memory. All the subsequent ones are blindingly fast because it's accessing the same stuff that's already there. So it takes 0.24 milliseconds. The whole thing takes about 5 milliseconds just to do this kind of distance check. So how would it look if we use the KD tree? And I realize I haven't shown you how to use a KD tree yet, but I do want to show you the results of what happens when you do use the KD tree. So the KD tree here, each individual cube is 0.009 milliseconds, that's 2 noughts. And then the total cost for all 20 is 0.08 milliseconds. So you've gone from 5 milliseconds, which is like over a quarter of our frame time, if we're hitting 60 frames a second, to what is barely noticeable on a profiler trace. So how does it do that? So the KD tree is a collection, it's a spatially organized group, it's a tree of points. That basically means that when it searches to find a point in space, it can very, very early eliminate branches in that search tree that are nowhere near where you're looking at. So it's a really, really optimal way of doing it. It does mean we have to build this tree every frame because our transforms are always moving. But actually the building of that tree is really, really quick and the querying is bursted, which basically means it can analyze and look at a large amount of data very, very quick indeed. So how might we use it? So again, I'm going to give you a link so you can find the KD tree if you want to. We're going to create another system. But this time we're going to put this one in the initialization system group. So this is right at the start of the frame. The reason we do that is we're going to be reading all the transforms and we don't really want anything else reading the transforms at the same time. Just going to create a type called KD tree. And what we have to do is we have to allocate the capacity. So we have to say the maximum capacity of this is these certain number of items. You don't need to fill that capacity. It's just how big it can be. That will allocate some memory. Helpfully, it will tell you on the console how much memory it's allocating. So for 1,000 items, using the default setup, you can customize some settings. It's taking 4K, which is not really that much. And then on our update, we're just going to build the tree. So we're going to have we're going to copy some points. So we're going to copy all of our transforms into a native array. Let's just assume we know how to do that now because we did that earlier. And then once we do that, we're going to pass that native array into this function build tree. And this build tree is just going to go and create this spatially optimized tree for you. We can see this is actually taken from Survival Kids. Survival Kids actually uses multiple KD trees. That represent different things. We have different categories for things that can be picked up for certain threats in the world. So here we do the copying. So this is where we have to copy all of our transforms, 0.05 milliseconds. Crucially, this is all on a worker thread, by the way. And then we build our building. Our total building is 0.06 milliseconds. Now, this is taken from my Windows development PC, but I artificially restricted the amount of worker threads that I had to 5. So my actual workstation could do 40 odd. But I've restricted there just to show you how well it parallelizes. So the total thing took about 0.11 milliseconds. But this is all on the worker thread. The main thread was just happy to carry on doing other stuff. And then to query, when we want to query, this is our new replacement function that uses the KD tree. We have isItem in range. We use the singleton pattern again, because I love it, to go and get the KD tree, and then we just call this function get entries in range. Now, in this case, we're just interested to know whether there is an item in range. We can, if we want to, get the results and actually look at what those items are if we wanted to. So we can, you pre-allocate how many you want. In this case, we said 10. It's guaranteed to give you the 10 closest items, but they won't always be sorted. So they won't always be sorted in distance order, but they are the closest 10 guaranteed. There's the QR code if you want to go and find it. If not, you can actually just search for Megacity KD tree. I know because I'm that vain, and you can find it. I am hoping to release it properly at some point or other. And the internal version that I've got has got a full suite of unit tests as well. But the version that's there is being well tested and is in shippable titles. So thanks for sticking with me for all of that. We'll do a quick recap over what we've covered. We're going to use systems to update, to call our update functions. Hopefully now I've impressed on you the importance of sorting those updates so that everything related is done at the same time. We can move transform access off of a main thread if we so want to. Don't be scared to look at scary black box Unity code and not want to try and replace that with something quicker, particularly if we want to do it in a burst job or move it off the main thread. And a KD tree can help optimize your spatial queries, and you're free to use it. Please do. So thank you very much for coming. That is my LinkedIn there. So you can, if you want to, hit me up on LinkedIn. We've got about 10 minutes for questions, so we will take some questions in a minute. I'm also going to be on the expert bar as well for the next couple of hours or so. So if you want to come and talk to me about anything, feel free to do that. But thank you very much. Thanks for coming. I hope you all have a wonderful rest of your nights.